You have fallen into Event Horizon with John Michael Godier. Dr. Daryl Seligman completed his undergraduate degrees in mathematics and physics at UPenn in 2015 and his PhD at Yale University in astronomy in 2020. He was a T.C. Chamberlain Fellow at the University of Chicago Department of the Geophysical Sciences after completing his PhD.
Daryl Seligman, welcome back to the program for, fifth, sixth time now?
Something like that. Thanks for having me back, John.
Now, Daryl, you have a new paper out, again, regarding dark comets, which is something that has been compelling my thoughts for the last year because it sort of helps to solve a scientific problem where we couldn't quite, used to be anyway, we couldn't quite tell the difference between an asteroid and a comet because they're sort of, it's ambiguous. An asteroid that outgasses becomes a comet when it gets a coma. And then a comet becomes a comet, but eventually it runs out of juice and becomes an asteroid. So now we're looking at dark comets, which sort of straddle that middle ground. But they also appear to be very interesting and may have implications on things like delivering water to Earth. Tell us about your new paper. Link in the description below.
Yeah, so essentially in the new paper, we discovered a bunch of new dark comets. And I think the main, just quick, exciting thing about the paper is we found a bunch more of these objects, and it appears that there are two distinct populations of dark comets within the solar system. So that's kind of the very quick summary of the paper.
Two distinct populations, explain that. So you see two different types in the candidates you've discovered so far.
Yeah, I think it's worth just giving like a brief description of what these dark comets are, and before talking about the two populations, what they are and how we find them, if that's okay too. So this kind of goes back to Oumuamua, the first interstellar object, which came through the solar system, and there were a lot of mysterious properties about it that confounded scientists. One of the main confounding mix of properties was that it had a non-gravitational acceleration that was very strong, which is an acceleration like what you'll see on comets when they outgas, because you're basically just producing a rocket-like recoil effect. But there was no dust coma whatsoever. So typically, when you have a comet that goes off and gets close to the sun, ice sublimates off of the surface and produces an outflow, and it brings small rocks and dust particles along with it. And that's what you see when you see a cometary tail, is those dust particles reflecting sunlight. And in the past, when we had seen comets before, you always identified them by those bright cometary tails. And so Oumuamua was strange because there was no dust tail, but it was accelerating like a comet would. And then since the discovery of Oumuamua, last year we wrote these two papers where we had discovered 7 objects that to be accurate, 7 near-Earth objects that were previously discovered. We didn't discover the objects. We discovered that they had non-gravitational accelerations like Oumuamua did with no dust coma. So we called these objects dark comets because presumably the only thing that could explain that we know of, the best hypothesis for their motion is some type of mass loss like outgassing of ices, like comets, but for whatever reason, there's no dust coma associated with them. And the way we identified these dark comets was that they had these non-gravitational accelerations. And the way you do that is you monitor their position in the sky over time. And then you slowly realize that as you get more and more data on their positions, that their positions can't be explained by an orbit that was just influenced by the gravity of the objects in the solar system. There has to be an additional non-gravitational forces operating on them to explain their positions. And then in this paper, what's so exciting, I think this paper is maybe even more exciting than the discovery of dark comets. We have discovered 7 new dark comets. So there's a total of 14 dark comets in the solar system that we know of now. And also, it appears that there are two different populations of dark comets just within the solar system. And that's kind of why our paper is exciting.
But that's like the asteroids because we have different populations of asteroids, right? We've got all sorts of classifications for these things at this point, but 50 years ago we didn't. We just knew asteroids existed. So we're seeing a sort of delineation, or classification of these newly discovered objects, right?
Yeah, and I think it's a kind of insightful point, John, just in general. I mean, not just with asteroids, but maybe with anything almost, like any scientific discovery. Once you start finding more of them, you can start picking out patterns in the data and classifying them or subclassifying them. And that the goal of doing that, right, is to I mean, scientists get things wrong all the time, but ideally it's like you can classify things in such a way such that they're classified based on something physical that's going on that tells you about their formation and their evolution and why they're important.
Do you think it's a problem in science today that we oversimplify? In other words, we look at objects, and stars and everything, we look at the universe and we sit there and say, well, this class is this way, this class is this way, but maybe it's more complicated. It's sort of like species on Earth. Yeah, you could say that's a deer, but there are how many different species of deer? And what are the differences and all that? And the only way you can tell that is by learning more and revising your knowledge. Do you think that maybe in certain areas anyway, that we're being too simplistic in what we expect from observation and that it may not be so clean cut? And in this case, you've got a comet that's not shooting off any dust. Well, maybe that might mean direct exposure of the volatiles to space and sunlight, things like that, and that there just isn't any dust to throw off. Do you think we have a situational thinking problem in science today, if that makes sense?
No, that makes sense. That's a really interesting point. I mean, my gut reaction, honestly, is to turn it back on you and say, I don't know if I'm really qualified to answer that because I think I've like specialized too much in certain fields to have a broad perspective on the question of if there's a kind of transcendental problem in different areas of science. So I would ask someone like you or somebody who broadly covered I mean, I would say you have expertise in a lot more areas of science and day to day cover more areas. So I think I would ask you if you think there's an issue going on there.
As a generalist with no qualifications whatsoever in anything, I would say that talk to your colleagues, cross-disciplinary.
Yeah.
Talk to statisticians and things like that. But maybe I'm off base.
No, it's a really good point. I think maybe well, you had alluded to before, there seems to be certainly, like you said with the asteroids. I mean, back a long time ago, we had comets and asteroids, and we thought maybe that was the end of the story. Then comets have ice and have these dust coma, and asteroids don't. And we've talked about this in prior episodes, but there's all of these things that are in between, these kind of hybrid objects, continuum objects that have some properties of asteroids and some of comets. And dark comets are an example of those that we've identified that are showing us that there's a lot more to the kind of puzzle than we realized before, because dark comets seem to have properties of asteroids and properties of comets. So maybe they are hinting at this larger problem of the classification. But I would say that in terms of trying to just spot patterns in data, we're doing the best that we can. So, I mean, right now with this new paper, for example, having identified now 14 dark comets, that's not that many. So we're trying to spot patterns in a pretty limited sample. So I think it's okay to try to spot patterns as long as we're understanding that we're just kind of at the tip of the iceberg right now, that there could be a lot that we haven't discovered, and we need to go out with an open mind and look for more.
So Daryl, until we can actually send out the geologist or the robot geologist to look at a dark comet, what can we infer as far as composition of these objects? In other words, how do they differ from something like Ryugu, the asteroid, where we find this carbonaceous object and then unfortunately accidentally contaminate one of the specimens with microbes? But then we see that, and we see things like one of the building blocks of RNA in it. But then we see chondrites, asteroid pieces that do not really bear so much of this. It's all just rocks, silicates, and iron. What do the dark comets look like as far as organic chemistry? Can we even tell anything at all about them? I mean, does that play into your thinking?
John, yeah, I'm really glad you asked that. So it's gonna be a you might not be happy with my answer, but unfortunately, we can tell almost nothing about these objects so far because even though they are near Earth objects, there is very limited data that we have on them so far. Just because there are a lot of near Earth objects, and we're trying to spot them all and make sure the Earth is protected from potentially hazardous objects. We don't have the resources right now to get detailed follow-up observations on all of the objects known. And what is kind of to me peculiar. So, okay, so something that is peculiar about the dark comets is that they are entirely unpeculiar. They are entirely uninteresting, except for the fact that we're realizing that they have non-gravitational acceleration. So these objects look like routine inactive near Earth objects. So they are so kind of like routine in what they look like that there has been no need to get follow-up for most of them anyway. That's maybe too much of an umbrella point what I'm making, but in general, they just look like typical near Earth objects and near Earth asteroids. So we haven't gotten detailed follow-up observations of them. So we know almost nothing about the compositions of these objects. The only things that we would probably say about the compositions of the objects would be if they're like other asteroids that we've studied in more detail, then they would probably look like X or Y. But then we've noticed now that these 14 objects are accelerating in these weird non-gravitational ways. And the first thing about this paper that I tried to do is just try to say, of what the limited information that we know of these objects, are there any patterns that we can identify about them? So compositionally, I would love to answer that question, but honestly, we don't know much right now. I can easily go on and on about all of the kind of James Webb observations or JWST or HST follow-up measurements that we could do of a dark comet that would be great and to answer some of those questions. But right now, we don't have any of that information. So in the paper, one thing just trying to do is like, based on the limited information that we have on these objects, what could we say about the population overall? And I think that's where we were trying to go with this delineation of two populations of them.
So you're getting to the point that you can see enough of a pattern to say we got two classes of object here,
Yeah.
right? Am I getting
Yeah.
that?
And so if you can show, yeah, sorry, I cut you off. Was there a question there that you were going to say? Or do you want me to?
No, I was gonna characterize it. Tell us what patterns did you see that allowed you to
Yeah.
make two different groups?
So if you can show, I mean, when you pull it up, like there's this figure that I made, which is figure 1 in the paper. If you can show that now, what you'll see in that figure on the left is a kind of zoom out of the outer solar system. So the red orbit on the outside, that's the orbit of Jupiter. And then the blue orbit is the orbit of Earth. And on the right side of the figure is a zoom in just of close to the Earth. And then you'll see in both the plots there, in the left plot, if you focus on that one, that's the zoom out. There are all of these orbits of dark comets in both red and gray. So the red and gray lines are the orbits of the 14 dark comets that we identified. Is it okay that I'm talking about this figure? Yeah, okay, you can pull that up.
Yeah. Ross will show it. Ross will show it.
And so then on the right, those are zoomed in just on the orbits around the Earth. So that's a lot more zoomed in. So the point here is that the gray and the red orbits, these are all dark comets, but they're color coded based on the two subpopulations or families that we're identifying. So the red ones are what we're calling outer, and I mean, maybe John, this gets back to your kind of an original, almost philosophical point about maybe are we classifying things too much? Is there some systemic problem in science? Maybe, and maybe to make matters worse, I just made up the name dark comets. I also just made up the name outer and inner dark comets. So, maybe someone will come out and find some reason why these aren't the best names for them. But I called just from looking at them, I looked at the red ones. I color coded them all red because I'm calling them outer dark comets because what it looks like is that these orbits are further out and they're also more eccentric. So the orbits themselves are more elliptical. Whereas the inner dark comets, which are in gray, and then you see them better on the right, those objects have more circular orbits, so less eccentric orbits, like more perfect circles, more closer to a perfect circle, and they're all closer to the Earth. So they have in kind of, or if you know some astronomy stuff, is the astronomical way of saying it is they have lower semi-major axis and lower eccentricity, but they're more circular and they're kind of closer to the Earth. They're closer in. So that's why I call them outer and inner dark comets. And then one other really important thing is it appears that the inner dark comets are all small and the outer dark comets are all large. So that statement assumes that they all have the same surface properties. So a lot of these objects, we don't actually know how large they are. All we know is how bright they are. But if you take how bright, so really the accurate statement is that the outer dark comets are much brighter than the inner dark comets. But on average, if they all have similar reflectance, so they reflect light the same way or they reflect the same amount of light, that's telling you that the inner dark comets are something like 10 meters in size, 10 or 15 meters in radius, while the outer ones are much larger than that. So the outer ones get up to kilometers almost in scales. Two of the ones that we found, these two of the new ones are estimated to have radiuses of 5 kilometers. And the other ones are hundreds of meters, whereas the inner ones are tens to 50s meters.
Now that's some interesting physics. So that would suggest that there's a physical reason for that, right?
Yes.
That you would have these two different populations of different sizes.
Mm-hmm.
Any ideas on the physics of that and how that could happen?
Yeah, right. So it appears that the difference, so just to summarize for myself almost more, the difference in the outer and the inner population is the outer ones have further out orbits, more eccentric, and they're bigger. The inner ones are closer in, more circular, and they're much smaller. And you're right. So the reason we try to classify it into two populations is exactly what you're asking, John, which is to see if there is some physical mechanism that drives that, and if that tells you something about how they form or why they're, is there something fundamentally different about those two different classes? We have to be a little bit careful because you could come back to me and argue, well, what if this is what astronomers call an observational bias, which means like, what if this is just the objects that you're able to see and there are more objects out there that kind of fill in the spectrum between the two classes and we just haven't found them yet? For example, I'm telling you that the outer dark comets are all larger than the inner ones, but they're also further away. So it would be very valid to say, what if there are smaller outer dark comets that we just haven't found yet? And so that is something that we definitely need to look into in the future. But the reason I'm saying this is because flip that on its head, you could also say, well, what if there were bigger objects in the inner population? And there's certainly, I can answer right now that if there were larger objects in the inner population, we would have found them. So the from this data that we have, one thing that I think is a real effect and not an observational bias is that the inner population of dark comets don't have any really, really large objects in there. So I think that is kind of like, if you're going to try to make a theory that explains what's going on or what's the difference in the physics going on, that's kind of one of the key things, is why is there no large objects in the inner population?
I think that if it turns out that that's correct, and after you remove biases and get enough of a data set, and that actually happens, that's some interesting physics, just basic physics. It's really interesting that might happen. Do you see it with the normal asteroid population, however? Can you look at, we have all kinds of different asteroids, Trojans, main belt, we've got all of this stuff. Did you find any correlation with normal asteroids with dark comet distribution?
That's a very good question, John. I'm hesitating to answer because it's a little difficult to answer because you have to be careful with what parts of the asteroid population that you compare it to. So I said that there is nothing special about these dark comets besides the fact that they're accelerating. The reality of the situation is that in the asteroids, it's one question that we'd have to look into in more detail is, did these objects look like they are just randomly grabbed from all asteroids? Or do they look more like a specific subset of asteroids or near-Earth objects? And that's something that would also, I mean, I think you kind of inspired me to do something now, but that would be something that would be worth looking into that I haven't done yet. But the reality is we know of lots of asteroids and near-Earth objects, and they come in all kind of shapes and sizes. So you'll see objects with orbits that look like the dark comets, and you'll see large ones and small ones. So I don't think, so this difference in the two populations doesn't look special when compared to the all populations of asteroids and near-Earth objects that we know of, if that answers the question.
As close as we can get.
Yeah.
As you point out, this is early in the game, and this is an entirely new avenue of thinking that wasn't even here 5 years ago. You invented it. You invented the dark comet, or the dark comet invented your thinking one way or another. It's interesting because, I mean, look, we know things outgas. Oumuamua did that, but we also know that plenty of other things do. Comets do it all the time as they cook through, but we also have these short period comets that are almost run dry, that they've just been around the sun so many times that they're running out of volatiles, but they're still producing dust. But yet the dark comets really aren't. But it's not hard to imagine how that could happen. And it sort of reminds me, you remember the hydrogen iceberg idea that you came up with Oumuamua, where you've got this relatively pure piece of ice, hydrogen ice, that's outgassing, but you can't really see it because it's hydrogen, not really much of a way to detect that. And it reminds me of that. Like, could the dark comets, let me put it plainly, could the dark comets be relatively pure as far as volatiles, but just don't have any dust?
Oh, I see what you're saying. And that would explain why we haven't seen any dust coma, you're saying, why they're dark comets.
Exactly. So, you got a comet that's throwing off dust. Dust is really easily visible. Yeah. You see it, glowing in infrared and doing all the sorts of things that it does. But if you don't see that, there are gases that are just really hard to detect. And nitrogen, hydrogen, things like that, just a little bit rough, to figure out if that's what's going on. And one of the main theories regarding Oumuamua is a nitrogen iceberg blown off a minor planet like Pluto. Not sure that I'm a fan of that, but okay. So it's just hard to detect, and maybe there's just no dust there. What's your thoughts on that?
Yeah, I mean, it's kind of like, John, it's like the $1 million question. So the reality of the situation is I don't have an actual answer for you, but I can speculate. So my speculation, the actual answer is we need better observations. I'm trying to get James Webb Space Telescope observations. Ideally, we catch one of these things while it's active and we can say what's going on. That's the great thing about these dark comets. Like, they're not like a Oumuamua. They're not gone after a couple of weeks. These things are around. In fact, one of them, we're getting the answer by 2031 because Hayabusa 2 extended mission from the JAXA Space Agency is going to 1998 KY26. So we will know the answer for at least one dark comet. But for now, I think that it is probably not the case that these are just very pure icy objects which don't have dust. I don't think that's right. The reason is so I'll back up for a second, but there is a budgeting problem about the dark comets. And this is maybe the weirdest thing about some of these guys, especially the inner little dark comets. So the first thing you have to say is, how long does it typically take for an object to go from the asteroid belt to an orbit like one of these inner dark comets? And the answer to that is something like 100,000 years. It's like 10 to the 5 years, okay? And then you can also ask the question, all right, you could essentially say, this thing, I see now that it is accelerating. How much is it accelerating? I know roughly how big it is. For the case of KY26, which is one of the inner dark comets, I know pretty much exactly how big it is. So you roughly know how much it weighs and how much mass there is. You could say for that size and mass, to make it accelerate, how much mass do I have to lose? And that gives you an amount of mass per time. And then if I say, how much mass does it have to lose over time, over the entire time that it's kind of been transitioning from the asteroid belt to the inner solar to the near Earth population, that 100,000 years, it turns out that it should have, all these inner dark comets should have lost all of their mass by something like 100-fold. So another way to say that is that if these objects are outgassing at the rates that would explain their accelerations, they should have they should have lost all of their mass in something like 1,000 to 10,000 years. Whereas we know that they've been in the inner solar system for tens to hundreds of times that amount of time. And that tells me that if it was a pure pure chunk of water ice or pure chunk of nitrogen ice or anything like that, it should be gone much quicker than the amount of time that it's been in the inner solar system. So I don't think that could possibly answer the question, because it's almost like it would be too active, if that made sense.
Yeah, well, sublimating ice. Very puzzling. Now, you said something that piqued my interest, Doctor. So, Hayabusa 2's next target after Ryugu is a dark comet. Did I get that right?
Oh, yeah. So we didn't, this was one of the original dark comets we found. So it's not one of the new ones, but one of the original ones in the original paper, 1998 KY26, is the target for the extended mission of Hayabusa 2. So in 2031, Hayabusa 2 will be rendezvousing with a dark comet and potentially impacting or landing on it. And Hayabusa 2, I mean, okay, we're not going to get another sample return, but it still has all of its instruments on board. So I'm trying to get James Webb Space Telescope data on these dark comets right now, but in a couple of years, we're going to have in situ, just the measurements are going to be just orders of magnitude better than anything we can get remotely. So we'll be able to figure out what's going on for sure.
I have a certain love affair with JAXA. Japan's space agency is the boldest experimentalists in the space field. Wouldn't you agree? I just love it.
Yes, I agree.
Ever since even Halley's Comet, back in the day, when I was 11 years old, they went and visited it and took pictures of the nucleus of the comet. And I've just always been a fan of JAXA, and I just don't think they get talked about enough in the pop science culture.
Yeah, no, I agree with you. I'm not a huge fan of JAXA, and I'm hoping to, provide any support that I can for their rendezvous with KY26, because it should be fantastically interesting and contextualizes this, new population of objects in the solar system and Oumuamua.
I am officially pumped because I didn't know that there was a connection between the next target for JAXA and dark comets. That's amazing. I am officially as pumped as I can get, which isn't really saying much. I'm a very calm person. But Daryl, so the idea of dark comets, though, and delivering water to Earth, and you mentioned that in your paper, explain that, because we don't really know how that happened. How Earth reacquired water and how we got these oceans. And perhaps these oceans that we have were once part of dark comets.
Yeah, and that's kind of what, you're getting at kind of the big picture of why it's interesting to study these objects. But you're right. So the reality is that we have a lot of theories, and I don't want to just say that we have no idea, because that will detract from a lot of work that a lot of people in a lot of different fields, ranging from planetary science to geophysics, oceanography, have worked on. And, it's not all my expertise, but we still are not entirely sure where the oceans on Earth, or at least the bulk of the water on Earth, came from. And, that's because there are chemical tracers, like, this is fancy sounding, but things like the deuterium to hydrogen ratio, or ratios of certain isotopes in Earth's waters, they kind of don't match what you'd expect, what you see in the interstellar medium. So the material that the environment that was around the sun, the protoplanetary disk that formed, the water there wouldn't have looked like that the Earth in where the Earth formed. So one hypothesis is that Earth formed and it acquired water later in its history. Potentially a popular hypothesis, but this isn't for sure, but there is some evidence for this, is that Earth acquired its oceans because it was hit by comets and asteroids. And comets, which had water in them, and maybe asteroids have some of them have water in them, there's a lot more asteroids that will hit the Earth, but every now and then a comet could hit the Earth. And those things in the early solar system delivered water that formed at much further distances in colder regions in the solar system. And so it was icy. And there's been a lot of fierce debate about the exact how this works, because at first, the natural thing to think is, okay, well, comet, this goes back to John, your original kind of insightful question about are we being overly classifying things, you say comets are things that have water and asteroids don't. So comets have to be the things that delivered water. But then we went with the Rosetta space mission and we were able to measure some of those tracers like the deuterium to hydrogen ratio and other isotopic measurements of the water in 67P, which is a comet that we sent a spacecraft to. And that also didn't match those that we measure in the Earth's oceans. So it's kind of still up for debate where the water is coming from. It looks like from measurements that we have of meteorites, it looks like a good possible area that it could be coming from is the outer asteroid belt. Objects in the outer asteroid belt seem to look like, just in terms of deuterium to hydrogen, that they match the water of the Earth's oceans pretty well. And then just at the very simplest level, and I can go into a little more detail about some reasons to believe this, but at the very simplest idea, if we don't really know where the Earth's oceans came from, but we think that they came from small bodies that had water on them, if these dark comets are hydrated, so they have water and liquid or volatiles and ices on them, and we never knew about them before because they don't look like comets, maybe they have played some part in delivering oceans to the Earth. We're not saying for sure they did, but we're just saying that it's possible that this is one of the missing keys in the puzzle that we're trying to kind of unravel where the Earth's oceans came from. And if it's really true that there are all of these objects in the near Earth vicinity that don't light up like comets but have water and volatiles in them, then it kind of makes sense that objects like these could have delivered Earth's oceans in the past. And another thing that's kind of important also is because they're really hard to detect, and you and I talked a little bit about observational bias. You only detect comets when they have coma. So if it turned out that there's a lot of dark comets ubiquitously throughout the solar system, but they don't have these bright tails, and it's really hard to detect the non-gravitational accelerations, dark comets could be really common. So we could start identifying them all over the place. So they might just, in sheer numbers, be dominating the population of stuff in the solar system. So maybe that's a reason why they could have delivered volatiles to Earth and the other terrestrial planets.
So we have a mystery, and I'm going to horrify Ross because he doesn't expect me to talk about this, but it was something that I thought about. The Tunguska event in the very earliest 20th century, where we had an object that was not quite like an asteroid, not quite like a comet, but looked sort of like a comet. You think, and we're being totally speculative here, the audience will forgive you for speculating, but do you think that a dark comet might have hit Earth?
I don't want to speculate on the Tunguska event specifically. Not really an expert in that area, and in terms of meteors, stuff like that. I think there are other people who could even speculate or hypothesize better than I can, but just in terms of could a dark comet in general hit Earth and produce something like the Tunguska event? Absolutely, it's possible that has happened in the past. So just to deliver water to the Earth, you would need something like that to happen. So I think in the early solar system, for sure, a dark comet could have hit the Earth. That's not to say that we are in danger of a dark comet hitting Earth now. It's more just that if it turns out, this is just like one of those things where we don't really know. We need to get some more data to figure out what the census of small bodies in the solar system is, but we've just discovered this new population. If it turns out that this is a very common feature of inactive looking asteroids that maybe, let's say, what if 10% of asteroids actually are accelerating non-gravitationally and we haven't spotted it yet? That's basically what Astor Taylor's recent paper showed, is that this could be a very typical thing that we're just starting to detect because it's very hard to identify the non-gravitational accelerations. That could tell you if it's about 10% of inactive asteroids that are dark comets, that, yeah, I mean, 10% of the natural extrapolation of that is that 10% of impacts on the Earth from asteroids or from dark comets.
So, speculatively, and this gets into existential crises, which are sort of my specialty in science, or talking about science. So, all right. So we have this population of dark comets, or two populations of them, and then we have the asteroids, and then we have the outright comets. Could we use, say, we need to deflect one, and we've spent a lot of time, researching deflecting asteroids so we don't end up as the dinosaurs. But could you artificially, uncover some kind of volatile on something up from a dangerous dark comet that's heading our way eventually and deflect it and make it artificially move instead of naturally moving around?
That's a clever idea. I don't see any showstopper reason that you couldn't. So I think it is theoretically feasible to do something like that. However, in practice, that it might turn out, I would suspect that it would turn out that that's not the most cost-effective planetary defense strategy, because the problem, I mean, right now, it certainly is not the most cost-effective planetary defense strategy because we have no idea what's causing the dark comet acceleration. Because we don't know what's causing their accelerations, then we would have no way of even knowing what type of impact or something we need to do in order to get the right type of outgassing to redirect it. So it would require your idea. It's a fantastic idea that you have. It would require a lot more knowledge about how dark comets are, like what they are and why they're accelerating. But I could envision a situation where you did exactly what you're saying.
Yeah, it's interesting.
Yeah, if it turned out that, dark comets had large reservoirs of ices in them and they were just very far deep beneath the surface, okay? I'm not saying that's the case. I'm just hypothesizing. That could be the case, okay? Then it would certainly make sense. Say you have an object. It turned out that there was an object that was a dark comet and it was going to hit the Earth. If you were to hit it in such a way that it kind of exposed all of that reservoir of material on the inside, then you could get a very strong impulsive thrust from the outgassing of that freshly exposed material, and it would save the Earth from the impact. That is a theoretically plausible scenario. I doubt that is something that would ever be easier to, I doubt that if there's anything that is in danger of hitting the Earth, I would expect that it wasn't a dark comet, just numbers wise. And then probably even if it was, it would be easier to just do something like the DART mission and deflect it ourselves. Yeah, it is not an entirely crazy idea.
I think it's an interesting idea because of the DART mission. So say that we did another one of those impact missions and we got more acceleration than we should have. In other words, it exposed the interior of the object that had more volatiles and it moved more than we thought. And I think that actually happened with DART, is that it moved a little bit more than what we were predicting. And yeah, it's an interesting idea. I would imagine the dinosaurs wish that they would have had impactor missions and have been able to do some.
No, you're totally right. I imagine they do too.
Yes, one imagines a lot of regrets on the part of the dinosaurs for not developing space travel.
Yeah, that would have been helpful back then. But more on a serious note, though, what you're saying is also science. Your proposal is also scientifically worthwhile, not even from a planetary defense mission, because I mean that's what we propose doing for an interstellar object like Oumuamua. I mean, if you could have impacted Oumuamua and exposed the interior and figured out what it was made of and got it to outgas, if it was really ice in there and got that to outgas, then we would have been able to solve the mystery of what was going on. So not just in terms of planetary defense, it would be worth doing just scientifically on a dark comet. And there was the Deep Impact mission that also did that to Temple 1, and that revealed subsurface volatiles, which then sublimated. So it's like, it is scientifically worthwhile to do something like that.
Yeah, I would imagine. I mean, since it's eminently testable, just send a bullet towards the thing.
Right.
You could falsify whatever hypotheses. You can go full on Karl Popper, and there you go. But I like it in that it's very physical, and I steal that from the geologists, because when in doubt, use dynamite to expose what you need to see. And I love these impact missions. I imagine a lot of people say, "Well, leave it pristine," but yeah, it's just a rock. It's just a rock.
Yeah.
Blow it up.
I mean, I think we need to recruit you to do some lobbying towards the government to put more in.
Do not put me in the position of NASA administrator. That would be terrible, because it would be all robotic missions to weird places. I'd be like, let's go to Callisto and see what's there, All right, Daryl, it's good to talk to you as always. And I look forward to more research on dark comets. What do you have coming up to continue your work, other than looking at it with James Webb?
Well, we are currently trying to get any observations and follow-up measurements that we can. We've got some data that's just coming down in the last couple of nights from the ESO's VLT, which is pretty exciting. And the biggest thing right now, currently, the National Science Foundation, my fellowship from the National Science Foundation is tied to the Rubin Observatory. So when Rubin and the LSST comes online, that's going to give us a huge increase in our sensitivity to detecting objects like dark comets or near-Earth objects or interstellar objects. So that's really the most exciting thing and what we're looking forward to in the future.
We've talked about it before. I cannot wait for first light of that telescope. Almost real-time observation of the stars. And the research potential just floors me. Even if you're just interested in variable stars, there's going to be data there. And it was just an unbelievable investment. Now we need one. We need them all over the planet. We need more LSSTs, one for the north. And, well, we kind of got that with Pan-STARRS, but we need more. And I'm hoping that that telescope shows us invest in this, because sky surveys are just all important. Thanks, Daryl, and I will. I look forward to the next paper.
Thanks, John. Thanks for having me.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.